we've been developing using addition and subtraction with fractions. We started off with fractions with the same denominator. Then we went to fractions with different denominators. Then we looked at how to translate word problems or word sentences into equations. And now we're going to look at applications. We're going to look at word problems. Let's work first with applications with one unknown. Now, again, to remember, here's the key to solving word problems. Hunt through the problem, find out what's given, and look for what's being asked. Then there will also be words that you can use, just as we talked about in Unit C, that will give you a hint of whether you add or subtract or multiply, and so forth. Then I love drawing pictures because for me, visualizing things is the most important. If I can see what's going on in my head, the step between that and algebra is much simpler for me. Then sometimes there might be a formula you need to use, like distance equals speed times time or distance equals rate times time. Anyway, let's start with a problem. A 2 1/4 inch nail is driven through a board 1 3/8 inches thick into another board. How far into the second board does the nail extend? Let's see what we're given. We're given a 2 1/2 inch nail driven through a 1 3/8 inch board, and we'd like to know how much the nail basically sticks out of the first board. Here's what we're given. The board is 1 3/8 inch. The nail is 2 1/4 inch, and we're asked the length of the nail in the second board. Here's the diagram, and you see there's the whole nail, 2 1/4 inches. In blue you see we have 1 3/8 inches that's going into the first board with that bit in gray with the question mark sticking out. And that's what we'd like to determine. How much is that quantity? We set that up because we know the whole length of the nail is going to be what's sticking in the first board, plus we'll call J, the unknown, what's sticking in the second board. 1 3/8 plus J is equal to 2 1/4. Let's try to solve that equation then for J. 1 3/8 plus J is equal to 2 1/4. We'd like to get J by itself. If I subtract 1 3/8 from both sides of that equation, what I find is that, first of all, I can get a common denominator by changing 2 1/4 to 2 2/8, multiplying the top and bottom by the quarter in terms of getting eighths. Then I just then need to subtract 2 2/8 by 1 3/8. Let's continue. I need to, if I have 2 2/8, I need to then borrow a little bit from the 2, so I borrow 8/8 from the 2, and I get 1 10/8, from which I subtract 1 3/8. And what I find out is that 7/8 of an inch of that nail poke into the next board or stick out of the first board. Here's another one. Your warehouse supervisor informs you that you have a total of 1 3/4 roll of a certain kind of paper. One job requires a quarter roll of the paper, another 3/5 of a roll of the paper, and a third 4/5 of the roll of paper. And the question is, are you overstocked or understocked? Do you have too much paper or not enough paper? And if so, by how much? Let's examine what we have and what we're looking for. Here's what we have. We have a total of 1 3/4 rolls of a certain kind of paper. One job requires a quarter of a roll, another 3/5 of a roll, and the third 4/5 of a roll. Do we have enough to do all the jobs? Here's what we're given. 1 3/4 on hand, there are the jobs. Do we have enough paper? What we have to do is subtract 1/4 of a roll, 3/5 of a roll, and 4/5 of a roll from 1 3/4. Notice that we have a problem here in that we have fourths and fifths. So we're going to have to change these things into fractions with a common denominator. The first thing I do is get rid of the mixed numbers and change the 1 3/4 into 7/4. Next, I then combine the fourths and the fifths just to make it easy for myself. 7/4 minus 1/4 is 6/4. Then minus 3/5 and 4/5 is minus 7/5. I've reduced this as much as I can without having to deal with finding a common denominator. I note that the least common denominator here is 20. I change the 6/4 and then I change the 7/5 in order to get 20 as a denominator. 6 times 5 is 30/20 minus 28/20. Now I can see right away I can do this. That leaves me with 2/20, which I can then reduce, in other words, change that fraction to lowest terms, dividing the numerator and denominator by 2, and find that I have 1/10 of a roll of paper left over when I'm finished. Therefore, I do have enough paper, and I can do the jobs with the quantity that I have on hand. Here's yet another problem. A travel agent is booking air travel for a family. The adult round-trip fare is $420, and the children fly at 2/3 of the normal fare. What's the cost of the tickets for a family of 2 adults and 3 children? First, here's what we're given. The round-trip fare is $420. The children pay 2/3 of the normal fare, and we want the cost for a family of 2 adults and 3 children. So in a sense, we're also given that there are 2 adults and 3 children. It was phrased as part of the question. Here's what we're given. We have an adult ticket and the child's ticket, and we're asked for the cost of 2 adults and 3 children at 2/3 of the normal fare. Here's the equation. We have 2 adults at $420 and 3 at 2/3 of $420. We now can do the math. Fortunately, if we have 3 at 2/3, notice here I have a 3 in the numerator, 3 in the denominator. 3 over 3 gives me a 1. What I wind up with then is 840 for the 2 adults and another 840 for the 3 children. So the total cost of the tickets is $1,680. Reasonably straightforward. Here's my favorite problem for this class. It's a poem. My towing rope was cut in half, and half was thrown away. The other half was cut again 1/3 along the way. The longer part, 10 meters length, is what I use today. But how long was my towing rope before this cutting fray? Very nice, heart-rendering, moving poem. But within that poem is a heck of a math problem. Let's take a look at it. First, we have to see what was given and what was asked. Here's what was given. The rope was cut in half, and half is thrown away. That half was cut in 1/3, 2/3 parts, and the longer part is 10 meters. How long was the towing rope before all this poem happened? Putting this in perspective, we have that we're given that the rope is cut in half, and half is gone, cut again by 1/3, and the larger part that's left is 10 meters. How long was the original rope? Let's take this in pieces. First, that orange line is the rope, and we'll say that the original length of that rope was L. Then we cut that rope in half, and we know that each half, one half is thrown away, and so what's left is equal to 1/2 of the original length, L. It was cut again by 1/3. So we've cut it again, and we have 1/3 and, of course, 2/3. What we have left then is 2/3 of 1/2 of L. That's the longer part that's left. We're getting there. If we have that 2/3 of 1/2 of L is equal to 10 meters, now I have an equation that I can solve for L. 2/3 of 1/2. 2/3 times 1/2, I multiply that out. 2 times 1 is 2. 3 times 2 is 6. So I have 2/6 of L is equal to 10. I can reduce 2/6. There's a common factor of 2 between the numerator and denominator. I finally wind up with the equation that 1/3 of L is equal to 10. If I multiply both sides of that equation by 3, I find that my original length of rope was equal to 30 meters. And remember, a meter was about a yard, so the original length of rope is about 90 feet, just to give you an idea of what we're talking about here. I thought this was a cute problem. I liked it. It made you think, and of course, I always like poetry in math, just like we saw there can be music in math. Now let's get a little bit more interesting in terms of some of these applications and talk about applications with two unknowns. What we want to do when we have two unknowns is we often have information that is understood. For example, you might have a formula or some kind of thing that you're expected to know. There are 3 feet in a yard, something like that. So you have to be careful in terms of what you're looking for. It may not be stated directly, but it might be something that you're expected just to know. For example, these are problems that I really like, and they're very typical of these problems in two unknowns. A daughter is 2/5 the age of her father. If their combined ages is 56, what are their individual ages? Let's look for the information. A daughter is 2/5 the age of the father. The combined ages are 56, and what's asked for are, what are their individual ages? Summarizing this, we're given that the daughter is 2/5 the father's age. The sum of their two ages, their ages combined, is 56. And we want to know what the individual ages are. Now you see here there can be two separate variables, but they're related to each other, because if we call one variable the age of the daughter, the other variable the age of the father, we see that those two variables are related by that 2/5. Let's continue and see how we would do this. By putting this into an equation, here are two things we know. D is the daughter's age. F represents the father's age. We know that the daughter's age is 2/5 of the father's age, and the daughter's age plus the father's age is equal to 56. We can't take any one of these equations and solve it just by itself. That doesn't work. We need both of those equations, and what we do is take one, put it into the other one, so we get one equation and one unknown. Here's how we proceed with this. We know that the daughter's age is 2/5 of the father's age. So if for the D in D plus F equals 56, I take what I know about the relationship between the daughter and father's age, D is 2/5 F, and for D, plug in the 2/5 F. Now I have an equation that I can solve, because it's only in one variable F, and I know that I can get that by itself. I have 2/5 F plus 1F is equal to 56. Let me rewrite that as 2/5 F plus 5/5 F equals 56. Somewhat of a tongue twister there. 2/5 plus 5/5 is 7/5 f is equal to 56. Continuing to solve that equation, if I multiply both sides by the reciprocal of 7/5 or 5/7, 7/5 times 5/7 is 1, which gives me f is equal to 56 over 1 times 5/7. I see that there's a common factor of 8 between 56 and 7, so I can divide a 7 out by the numerator and denominator, again making this a little bit easier to do. You don't have to do it this way. You could certainly get the improper fraction, 56 times 5 over 7, and then change that back to a mixed number. You'll wind up with the same thing. But if you observe these things ahead of time, you'll be able to save yourself some calculations later. So we're showing you the methodology for doing it, but again, there's always more than one way to do these, and you should find the way that's most comfortable for you. Anyway, so much for my little lecture. Let's continue. 8 times 5 is 40, and I find out that the father's age is 40 years. Well, I'm not done yet because I'd also like to know the daughter's age. I remember if the father's age is 40 years, the daughter's age is 2/5 of the father's age, or 2/5 of 40. I see that that's 80/5, or 16 years. Is this correct? The father's age is 40 years, the daughter's age is 16 years. How can I check this? What I can do is remember that one of the facts we were given was the daughter's age plus the father's age is 56. Is this correct? 16 plus 40 is 56, and this makes me think that there is some slight possibility that I did this correctly. Let's look at one more. The owner of a store predicts that a second store she'll open will earn 3/4 of the amount her first store does. If she's hoping to have sales totaling $90,000, what will each store need to take in? Let's mine this for information. We know she sees that the second store will earn 3/4 of the amount of the first store, and the sales from both stores total $90,000. We want to know what each store takes in, how much money each store earns. Summarizing, we know that we'll call the stores A and B. A is the first store, B is the new store. The new store is going to earn 3/4 of what the first store did, and between the both of them, they're going to earn $90,000. And of course, what we want to know is what's A and what's B. What are each store's sales? Let's put this into the form of two equations. We have B, the second store, is going to earn 3/4 of what the first store does, and between them they earn $90,000. Again, we now have two equations, if you look at this, in two unknowns. We have two relationships. And if we just look at either piece of the information, we see that we can't do it. We need to combine them. Here's what we do. Again, we take B, the value we get for B, 3/4 A, that piece of information, and plug it into the sum. So we have A plus 3/4 A. Now I have an equation and one unknown, and I can solve this. The same as I did in the last example, 4/4 plus 3/4 is equal to 90,000. 7/4 of A is equal to 90,000. I can continue with this now and multiply both sides of that equation by the reciprocal of 7/4 or 4/7. When I solve this, I get that A is equal to 90,000 over 1 times 4/7. And again, I can do the math and find out that A is very close to $51,430. Then, if I know that that's A, and I know that A plus B must equal to 90,000, I can then just subtract that from the 90,000 and find out that B is got to be $38,570. Pretty good. Let's look at another one. We're just going through a lot of problems here, and watching what I do and how I solve them may help you to think about these things I'm trying to explain as I do them, as carefully as I can, what's going on in my head and what's going on in the heads of many other people who solve problems like this. Two friends agree to meet to talk about their Math 86 homework. What else? One jogging leaves her house at 5 miles an hour. The other driving through traffic leaves her house at 25 miles an hour. How long will it take them to meet if they're 3 miles apart? Let's assume, of course, they're going in opposite directions so that one isn't chasing the other one. For example, I can envision, oh, never mind, the jogger trying to follow the car in the same direction. It'll take them a long time. Anyway, so here's an assumption we make right there. Let's look at the information. The jogging person leaves his or her house at 5 miles an hour. The other hops in the car and goes 25 miles an hour. They're 3 miles apart. We're given, there's the information given, and we want to know how long before they meet. The problem here is that you have almost, but not quite, all the information you need to do this. There's something you also need to understand, because the distance, how far you go, is how fast you go times the time you're moving. And we're talking about distances here because they're 3 miles apart. And so we have the formula that we need to use here, that the distance is equal to the rate times the time. Let's fill things in here. First of all, student A leaves at 5 miles an hour. Student B leaves at 25 miles an hour. What do you know now? Here's the key to the problem. They both leave the house at the same time and travel until they meet. Hi, let's do some homework. So what we know is that they both travel exactly the same time. It doesn't matter how far they go. The one driving the car is going to go further than the one jogging. But since they've both left the house at the same time and they both meet, they both will travel sometime t, and we don't know what that is. But we do know what the total distance is. The total distance is 3. One travels 5 miles an hour times whatever the time is. The other travels 25 miles an hour times whatever the time is. And since they're 3 miles apart to start with and walking together, we know that the sum of how far they travel has got to be 3 miles. 5t, the distance the jogger goes this way, plus 25t, the distance the person in the car goes this way, that total distance, as they've started 3 miles apart, that total distance has to be 3 miles. So now we have an equation that we can solve for t, the time. 5 plus 25, 30t is equal to 3. T then is equal to 3 divided by 30, dividing both sides, or t is equal to 1/10 of an hour. We might want to ask how many minutes it is before those meet. Well, if 1 hour is 60 minutes, 1/10 of an hour is 1/10 of 60, or they meet after each of them has traveled 6 minutes. Of course, the one in the car is going to go a lot further in that 6 minutes than the jogger. It really helps in cases like this if you were to make a diagram and actually even have dolls or little pieces of paper you push around to help you envision how these things might work. Here's another car problem. A car leaves Phoenix traveling at 50 miles an hour towards Tucson. Another leaves Phoenix traveling at 70 miles an hour towards Flagstaff. And now we have cars that, again, we need to visualize. These cars are going in opposite directions at different speeds, and we'd like to know how long it takes them to get 250 miles apart. These are your archetypal algebra problems. Whenever you have people joking about algebra problems. These are the kinds of problems they joke about, and they look annoying, but they're really not hard if you try to get a good picture of the situation and find out what's equal to what the totals are, and so forth. Let's continue with our analysis of this problem. We have a car leaving Phoenix going towards Tucson at 50 miles an hour. Then we have another car traveling north towards Flagstaff at 70 miles an hour. And we want to know how long it will be for them to be 250 miles apart. Now, we're assuming also, remember, that they've left at the same time. Here's a little diagram, not very clever, but we want to know where they are 250 miles apart. There's what we're given, just reviewing it, and here is what's asked. How long until they're 250 miles apart? Let's fill in on a table what we know. One is going 70, one is going 50. Since they've left at the same time, we know that they're going to be traveling in opposite directions for the same time. For one of them, car A goes a distance 70 times t, where t is the number of hours. Car B goes 50 miles an hour, travels 50t. We know that the distance is the rate, how fast they go, times the time, and that distance is 250 miles. We have the 70t, that's how we know they're traveling equivalent times, plus 50t is 250. Working this out, I have 120t is equal to 250. T then is equal to 250 over 120, and I try to simplify this, divide top and bottom, numerator and denominator, by 10, and get 25/12. I find that t is equal to 2 1/4 hours, 2 1/12 hours, I apologize. Now let's see, 1 hour is 60 minutes. What's a twelfth of an hour? It's 5 minutes. Therefore, to get 250 miles apart, those drivers have to go for 2 hours and 5 minutes.